thermal limits. In this, in fact, the thermal balance is being influenced by two main factors. The first factor is the heat that is coming for the current flowing inside the component. And the second factor describes how the surrounding medium has the ability to decrease that heat. In particular, the maximum capacity, the maximum current that could flow inside the component is proportional to the delta in between the temperature of the ambient and the maximum temperature of the components. So, means if the ambient of the temperature started to increase, the capacity will decrease. However, climate projections point out that the temperature of the ambient will increase, probably will increase in the next decade. Meaning so that now that this delta for 2050 will be smaller than 2030. But however, we don't know how much it's going to be. So that raises my first question. How can we project reliable thermal limits for the next decades? Before we start to explain a little bit the method, let me explain three fundamental concepts in this investigation. The first is the ampacity. The ampacity is the real maximum current that a component can carry out safely. So could be calculated or monitored. And here you will see it in blue. The second is the rating. The main difference in between ratings and ampacity is that the rating is a value selected by the operator. So that means if I have a really conservative rating here, we could be under efficiency. However, if I select more dynamic rating, I could be in a risky zone. So how can the transmission capacity could be extended safely? In order to address this, over 3 decades before, a concept of dynamic ratings has been existed. This concept is mainly related with the weather-dependent capacity, so the use of this, and a component a lower maximum capacity allowed by the operator. So the second one. However, this concept is mainly related with short term. So that raises a challenge. How to develop in advance thermal ratings without compromising safety? So now we establish the fundamental concept. Now let me show you the full landscape of the context. This thermal that you see here is mainly divided by the three main components that this research investigates and the main subjects of the research. So let me explain a little bit. Here in the first column, we could see that the thermal models are really well established and standardized. Second, we see that mostly all of the work have been done for overhead lines. And the third, that this work has been doing for short-term operational planning. So that let me show clear methodological gaps. First, your studies integrate dynamic thermal rating with the long-term plan. Second, there is no standardizing method to include dynamic weather ratings with risk-aware planning. And the third one, and the most important one, also the climate change are not directly influenced inside the rating. So now that you can see here all of the landscape of my research, let me show you the key studies. So it's important to highlight that there are really studies that understand or analyze the interconnection between climate change and capacity. The first one is Bartos. Bartos analyzed all the weather lines in the United States using representative concentration pattern. He found out that the capacity in mean in the United States would be reduced to 6% by 2050. The second study is in UK. Cradle analyzed the overhead lines using 100 weather generator scenarios for 2050. She found out that, for example, for the month of summer in 2050 will decrease the capacity. The third study that I showed you here is a study that not only analyzes the capacity of the component, but also the penetration of PV. we find out that using representative concentration pathway, the business as usual scenario over 2,100, the PV could increase by the use of TTR over 45%. However, as you can see here, all of these studies have been focused in overhead lines, and probably there are not fully represented declines. So in that, can we fully represent the future climate in order to analyze the capacity and power system of all the components? The second study is related with DTR with probabilistics. The first study is a study in overhead lines made by Lewis. The important part of this study is that he released a new concept of DTR. It's called quasi-dynamic rating. So, in order to do that, he introduced cumulative distribution functions inside the ratings in order to let the operator introduce the risk. The second is a probabilistic management of the risk. So, here, Bracali introduce a probabilistic forecast for demand and generators in order to control the risk inside the power transformer. He found out that doing this methodology, it could reduce the economic losses over 65%. The last one is a method that also uses probabilistic distributions as Douglas, but this time, he selects a time-based subset for the time. So that means that now you have the possibility to select monthly, hour, frequently. We find out that using this, the capacity will increase over 30%, meanwhile controlling the risk. So now, beyond starting to analyze the capacity, we need to see how is the rating increased with the risk, however. The first is Badger. Badger introduced a robust control inside the rating using a probabilistic constraint. So he found out that doing this, the cost could be reduced over 8%. The last two papers are related in how to introduce the thermal balance inside the constraints of the optimizations. So Lee and Kirikelko shows that when you start introducing in order to control the maximum temperature of the component, even in extreme weather, could be reduced over 1% the cost. However, all of these investigations have been focused in overhead lines and in short term. So all these insights shapes my contribution objective. The main objective of my thesis is to develop a methodology for long-term power system planning that incorporates the interrelationship of three main concepts: thermal ratings, network planning, and climate change. It will be addressed by 6 questions. The first question is in order to know how to calculate the thermal rating in advance, including variability and capacity. The second is the next 2 questions are related to how to introduce these ratings inside the network planning. And the third one, how will the climate change impact using the previous 4.1. So until here, we have established the context and the main question of my research. The following slides will be focusing only answer one question: how we could calculate in advance the rating for the next decade. So first, we need to. It's important to highlight that in order to calculate the ratings, first we need to calculate the capacity. And in order to calculate the capacity, we need to use thermal models. And here is the most used and the most studied one. It's the thermal model for overhead line. That is mainly governed by the thermal balance and is influenced by the temperature of the ambient, solar radiation, and wind speed. However, as we know, overhead lines could be extended for many, many kilometers. So, in order to address this methodology analyze the spatial variability of each segment inside the line in order to find the worst condition. The next thermal model that I'm showing you here is the underground curves. The main difference in between the underground cables and overhead lines is that now the heat exchange is occurs with the soil. The second is that mainly this component is installed over 80 centimeters and even to 5 meters. And the third, that the thermal balance formulation is mainly influenced by the soil temperature and soil moisture. However, this thermal model has a challenge in between. We need to find a resolution for these two across different regions in order to calculate it. So, in order to understand this, first it's important to highlight that the physics behind the temperature of the soil and the moisture of the soil are non-linear and complex. And mainly is influenced by the soil composition and sulfate methodology. So, in trying to find the data in order to gather this, it's not an easy task. For that, I use my first method of even solution. I will use it in one into soil classification and sulfate methodology in order to predict the soil of the temperature and moisture. And now we have the opportunity to calculate the thermal resistance of the surrounding soil across regions and across time. So that means that if the operator wants to calculate the capacity of the example, they use this for the next decades. Now we have our last thermal model, is the power component. This thermal model is really influenced by the solar radiation and the temperature climbing. And the key factor here is the wind factor. So here we use well-known and standard in order to calculate capacity. However, it's mainly modified in order to introduce the influence of the solar radiation. So, at the end, we will how to calculate capacity by the use of thermal model and the weather. And still, I didn't answer the question. How are we going to calculate the in advance? The current system is like thermal methodology. And if we focus in a trade-off in between maximization of the transmission capacity, meanwhile controlling the things. So, let me tell you how I do it. It's a five-step step. The first, for the specific location of the conflict, I gather the only economical variables. Second, by the use of the specific thermal model, for example, over the time, I'm going to calculate the capacity. So here, in this specific figure, you see the calculation of the capacity over 50 years. After we have all the simulation, now we have the possibility to divide it by a specific temporal subsets. For example, monthly hour, month, or year. With that, we are going to focus in the low detail of the distribution of the subset in order to gather the experience. So, let me show you here the picture. Here we have a 4-year capacity calculations. Here, each color is a subset. Here it is monthly. And in this subset, we focus in the low detail, so you see the red dots. Now, with this observation, we have the possibility to fit it inside the power law. This is mainly because using that, we could use a lower threshold limit that will be related to limit exposure to extreme climatic events. So, now this represents here, we are going to feed the result that you see in the blue dash. So, here, we have a periodic distribution for temporal subset. So with this, and with a specific lower threshold that could be 1,000, we fulfill our quasi-dynamic thermal ratings. So let me explain a little more this figure because it's important. So here we have an example of ratings that in order to build this, we use a subset monthly hour. So I will describe monthly hour. In that, we specific a low threshold that is going to be 1 per thousand, and with this threshold, we could build different ranges across months and across hours. So now we could represent the whole year. So another thing that you see here is the seasonality. that government and rating. Government review credit and fee control. So,
because of the problem of the sound,
yes.
time on the 45 minutes. Can you try to don't use this one and speak close to this?
Of course.
Because if
It's echo.
yes, maybe you
But
don't
close. I cannot move from here.
One second. First of all, let's see if they hear.
Hello, professors.
Yes, it's much better when you use the this one.
Okay, let's do like this then.
So I'm gonna stay here.
Yes, please.
I'm not gonna move.
Yes.
Sorry for the.
No.
I will do like this, okay?
The audio visual.
Okay, sorry. This is research.
I'm gonna have to show.
So until now, going back, until now we have established how to calculate the ratings in the next decades. And here we find the first result for the first methodological contribution, that is to asset a machine learning model in order to project the soil moisture and the soil temperature. So in order to do that, I trained 5 machine learning models using all the soil composition observations, surface methodology, and observation for 32 stations. With that, we see that with the result of these machine learning models, we also not only improve the variability of the variable, for example, but also we improve the accuracy. So as a result, now we could project also soil temperature and soil moisture for the next 50 years if we want. The second is the QDTR performance. So in order to see the performance, in the left part, we see the trade-off of QDTR, higher rating, lower risk. And here we see the possibility that select different kind of time scales. So let me give you an example. Here we have an overhead line. Here in the previous, in the gray one, we have the results of the opacity. But here is the QDTR calculated in a monthly hour. So now we only not only expand the maximization of the capacity, but also we could reduce this risky zone that could be overheated the component. The second is the thermal performance of the QDTR. So let me explain this slide. We could see 3 things. First, that is time dependent, meaning so that have the possibility to select monthly hour, as I showed you before. The second is the seasonality. Colder month, maximization of the rating. Other month, reduce of the exposure to the climate change, And the third thing that we show here is the difference between models. So underground cables, as you see here, is reduced variability, and it's mainly by the influence of the soil inertia. The third result is a spatial performance of the QDTR. Sorry, I was moving. Of the QDTR. So to do that, we ran the same previous methodology, but this time across Europe. So that means with the 0.25 resolution and over the last 50 years. With that, we could see some interesting things. First, underground cables rating is mainly strong. It's mainly connected at the strong influence of the soil taxonomy. For that reason, you see all this variability of the ratings. The second, power transformers. There are more pronounced in some regions, the results of the rating, and mainly because, if we remind, this thermal model depends mostly in the ambient of the temperature. So until here, we have the summary of the first chapter. So what was my motivation? I need to calculate in advance the rating. How I did it? 2 contributions. First, in order to gather the information for underground cables, a new model to estimate projections, soil moisture and soil temperature, in order to calculate the thermal resistance. And the second and the most important one is the quasi-dynamic thermal rating. This is not only a methodology, this is a rating description that should be integrated inside the dynamic thermal rating. With this, we could maximize the capacity, for example, 22% in power transformers in a regional way. And second, meanwhile, controlling the risk, because I have to say that all the previous results that you saw is with 1 per 1,000 lower threshold risk. So until now, I established the tool or the methodology in order to calculate the rating number. The second, in the next slides, I will focus on how to integrate this thermal rating inside the network plan. So here I'm bringing to you a typical network expansion plan formulation as optimization project. So this optimization aims to reduce, to minimize the system cost. However, it's important to highlight here that it's mainly focused in the control the capex of line and power transformers and no generator. And we did it because we want to. I want to isolate the influence of the QDTR. So a little bit of this here, how it works for each network component. For example, underground cables, overhead lines. I'm going to calculate the QDTR, that's a cumulative distribution, and I'm going to fix a specific lower threshold. As I said, normally all my studies doing with 1 per 1,000. And with that, we're going to replace the maximal limit constraint inside the thermal limit constraint of the optimization. So let's see the results of this. First is the impact of the QDTR using a specific network expansion plan now with the library of PIPs. It's important to say that even PIPs that we managed to simulate to the QDTR over all the regions that you can see here. The way that works with PIPs only let to use QDTR across interconnection, so reduce quantity of lines. For that reason here, you even with that QDTR only interconnection, we visualize that the system cost will be reduced using QDTR with a thinner resolution here in Montreal. The second is in order to overcome the limitation of PIPs, I decided to move to a specific network test case. So as you can see, the 24 nodes here is projected now in the south of France, and is included the QDTR for lines, underground cable, we replace it here, and overhead lines, and analyze it typical 2 cases. So this result is very important. First, because capex reduction. So that meaning that with the use QDTR with a thinner resolution, we don't need to build more lines. However, the second result that now we have a PV penetration, we see that now the QDTR highlight the dangerous zones when we have the probability to have high flow caused by the PV and reduced rating caused by the seasonality. And at the end, that means that we need to build new lines for these 2 consequences. Now we're moving from macro to micro. That meaning that now we analyze the impact of QDTR in lower voltage distribution networks and middle voltage distribution networks. In the future energy transition path, that means that we have now high increase of PV and charging stations. So the result here in the case A is that using the QDTR with a thinner resolution, we could reduce the total violations by night times. You know, when the people arrive home, you need to connect and charge the vehicle. The second, case B and case C is a medium voltage. We see the same result as previously. So that meaning that we confirm that using the QDTR in the cases that only we increase the demand, the investment is reduced, so no lines. But also, when we use QDTR, when we have high penetration of PV, we highlight and identify dangerous situations. And at the end, it will end in a new investment inside the lines. So we need to make a stop here is because all the calculations that you have seen before, I need to highlight that have been done with QDTR. And the QDTR, in order to calculate it, we remember the thermal balance equation is mainly with maximum continuous loading and a fixed threshold, 1 per 1,000. However, this is too conservative. So that kind of detail is mainly what my investigation want to overcome. So for that reason, it's coming my third methodological contribution. That is a more precise temperature-based constraint method. So let me explain this title. So as a QDTR, the component should be worked always in the safe zone. The safe zone is below temperature maximum. However, it's possible by a few hours extend this zone to a tolerated risk zone by a delta of temperature. So now the component not only could work here, that is our conservative area, but could be extended in a small area here in a yellow. If it's working in the red shadow, meaning that now the component has the high probability to reduce the lifespan or compromise the safety. So I'm going to explain it more in detail. So for now, we are going to, in order to that, we calculate the cumulative distribution for a specific line in order to gather all the current flowing. For each values of the cumulative distribution in that specific line, for example, we are going to use and remember our thermal balance equation, gather the information of the weather and the rating in order to calculate the temperature. So now with a different sets of a specific weather related with that specific point, we're going to calculate the temperature. And we do that for all the current distribution. With that result, we could build our cumulative distribution of the temperature that you see here in yellow. However, if the result is not this yellow, is this yellow shadow one, meaning that now we are in the risk zone, a control should be done, and the control is reduce the rate. So from the graph, we are coming to a flow. So let me explain the same methodology now with a flow. From a specific scenario input, we calculate the QDTR plus a delta temperature for each time step. For each time step, we are going to run Monte Carlos using optimal power flow plus optimal power flows with contingencies. With that information, the result of the Monte Carlo, we could build density functions. So here, for example, we see the density function result of the power flow normal. And all these are the density functions of each contingency over the line. Why we do that? Because now with that, we're using a specific weighted density function, we could calculate our final current density function. Why we need that? Because with that, we could use the cumulative distribution in order with a set specific temperature in order to calculate the risk. So at the end, if the risk is in the no risk zone, the rating will be replaced inside the network plan. If not, we need to reduce the rating and start again the procedure. I need to remind that this procedure also will use auto sample in order to clarify that the results is correct. So let me show the results of this methodology. So for this, we use our test case, it's similar test case, but this time with our risk management control, and the optimization will be expanded a little bit in order to include a multi-period optimization. So we have the results, but before I need to explain a little bit this chart. Left columns are QDTR calculated yearly in the time yearly. Right column, QDTR calculated monthly hour. Yellow results means the results of the use of a static thermal rating. The conservative that say that we need to use 40 degrees, for example, as the temperature. And the second is the power flow as a result for the QDTR yearly using the methodology that I showed you before. So 3 behaviors to show here. First behavior, in the specific lines, by the use of the QDTR yearly, we show the same contribution that I showed you before, reduction on the investment completely. It's not necessary to do an investment, a new line in this specific line. And the second behavior is more complex. It's showing that using the static thermal rating in another line, because it's the 18 and 22, we need a new investment. But here, the rating starts with a specific calculation, but before the investment, it's going to be constrained so enough to be held until 2040, and 2040, we need a new investment. So here, we delay the investment using the QDTR with risk control. And the third one is now the same line, but with a thinner resolution of QTTR. So imagine here we delay, and here we start again. We reduce completely the investment, only selecting a thinner resolution of the QTTR. So meaning that when we change thinner resolution, but we include the risk control, we could reduce all the investment over the case. So as a summary, question, how to integrate the QTTR inside the network planning? To answer, first is the first method is going to be introducing the QTTR to replace the rating directly inside the network expansion plan. And the second, temperature-based, more constrained method in order to calculate it, the rating. To highlight, we use this case in different network expansion planning, and we found similar results, meaning that showing the performance of the QTTR. And the last, that if we use the risk control, we could delay investment and also reduce if we change only the resolution inside the QTTR. So until now, we have established how it's going to be the thermal rating methodology, how to introduce it. And now we need to answer a question, how to include the climate change and how it's going to be the impacts. So it's important to highlight that all the calculations that I showed before and every result that I showed before is with historical values. However, if I want to analyze a network today or plan a network today, must work in the next decades. And we know that in the next decade, the temperature is going to rise. So how we found a solution about that? So my framework, my new framework here, introduce all the methods that you saw before, risk control, QTTR. However, we change the data. Now the data is a future data about climatic conditions. For this, we are using a specific data, the climate and energy indicator for climate projections, as a proxy or best information available for long-term climate conditions. So let me explain a little bit more this data. So this data is made according to the representative concentration pathway and corresponding to the radioactive forcing that is related with the CO2 emission and the greenhouse gases emission too. So also this data set is important to highlight that have a link with the electrification. So let me explain more about this. So we are going to take as example the business as usual or the worst case representative concentration pathway that is 8.5. In the 8.5, we are going to have high temperatures. If we have high temperatures, meaning that now the power system components is going to be more stressed. However, in this scenario also is included how we are going to make the electrification and how it's going to be the transition of the energy. Meaning that in this scenario, we're going to use more coal and less PV production. So for the side of the flow, the network is going to be less stressed. However, if we took the best one or the most optimistic one, that is 2.6, it's contrary. We have less impact of the temperature, so less stress at the network by the temperature. However, now we have a higher imposition of the PV and wind, for example. That makes that now the network will be stressed more by the flow. So let's see some results of here. So this beautiful heat map table is divided by 3 columns. Each column is related with a specific power system component projected in the south of France. And each row is a representative concentration pathway that evaluated. So what we could see here, first, is that underground cable is going to be this specific underground cable is going to be the less impacted by the weather, as I told you before, mainly related with the solar inertia. Second, the most impacted one is the power transformers. However, in this specific power transformer are framed by a specific reduction during a specific hour and a specific month of the year, mostly because related with the temperature. And the third one is most of the year, most of the representative constellation pathway, we're gonna have like reduction of the capacity. So the following results, we use the same methodology that you showed before, but now we do it in a continental case. We use the RCPs in order to calculate how it's going to be the QTTR in 3 main components. So the same structure. What we can see here as a regional pattern before was a specific power system. This is regional pattern. As a regional pattern, we see that the low impacted still is the underground cable, confirming the hypothesis. Second, that the power transformers are the more stressed about the climate, even to 5.5. But however, as I say, we can see that some region, for example, south of France, the south of Spain, will be more impacted than other regions. And mainly because, as I said before, is influenced mainly about the temperature of the animal. And the third thing that we see here, that all cases we saw reduction. So that meaning the climate will reduce in different scales, but will reduce the capacity of the network. And now we analyze how it's going to be the climate impact in system cost. So we use the previous network expansion plan, we use the PIPSA in order to analyze projections. As you can see here, is a result in the difference between historical and representative concentration pathway for future scenarios. We see that if we calculate the expansion plan with historical, we are too optimistic, meaning that we overestimate the capacity, the transmission capacity, meaning that now we need to spend more money, spend more investment in the future using the representative concentration pathway. The second result that you see here is now the same test case, but this time the RCPs are not using only to modify the rating, but also to influence the profile of load and renewables. So we could see here, there are 2 lines that are congested. In the bottom part, right part, we see that the climate will reduce the ratings. But remember that this is a risk control. So here, the reduction is not only by the weather, it's also by the expansion of the grid, depending on the network expansion planning accordingly to RCPs. The second part here is if we plan with historicals, we are too optimistic. So meaning that we overestimate the capacity, meaning that in historical we don't need investment. However, as we could see here with the RCP scenario, we need it. So here are the full landscape of the previous result and the historical one. So in this full landscape, we see 2 things. Thinner temporal resolution using QTTR allow me to reduce the investment. And second, when we evaluate our network using historicals, we continue being too optimistic about the results, and we overestimate the rating capacity. So for that reason, we see that the investment started to increase using the specific scenarios. As a summary, my motivation here was involve the climate change inside the 2 methodological results previously. The contribution is the integration of climate projection inside the RCP and in the other methodology that is more constrained temperature based. To highlight, capacity will reduce over the 3 scenarios by the temperature, and also even if we use the risk control. And the third one that's also really important, if we use historical, we are doing a too optimist result as a scenario. For that reason, we must include the future projection condition in order to plan. So, conclusions and perspective. So, I show you my 3 subjects that are going to be interact and the results here. How can we calculate in advance the rating in the spatial variability of the weather? The result is QTTR new definitions. With this QTTR new definition, we not only maximize the capacity, but also we control the risk. And for example, in the in this, we analyzed the Danish region. We could even increase the capacity over 22%. The second, how we're going to integrate the QDTR, we analyze the network expansion plan in modifying the maximum capacity inside the optimization problem using QDTR. And the second is the risk control management method. That is a new method in order to include the temperature and let us to expand a new tolerated risk areas to calculate, modify the maximum capacity inside the optimization. And also important to see here is the influence of PV. The influence of PV, if we use QDTR, that led me to highlight this dangerous zone that is not only by the weather, but also by the flow. Third one is climate change. As we could see before, the climate will impact all the three components. If we analyze as a European continental scale, power transformer will be the most influenced one with a reduction of 2.1. And the third one is really important. It's like we don't have to plan with historical. We need to include the climate change inside our optimization in order to plan in the future our networks. Perspective, of course, there are so many perspectives. First of all, it's important to update to new climate data set that let us to identify more regions. And now with, for example, with socio-economical pattern. Second, in the same one, as we did with underground cables, in order to improve the variability of the soil temperature and soil moisture, we could do it with wind, for example, in order to improve the data set. Second thing over here is, as you could see here, all my results have been done with one specific climatic scenario. In order to be more precise with the uncertainty, we could include a multi-model ensemble, so different kind of climate models in order to assess the capacity. Third one, incorporate the sensitivity analysis across available climate support in order to have a better selections. The introduction of a COPF now, because we started to scratch distribution, so it's important to calculate the losses inside the optimization. This is because the Monte Carlo solution is our first contribution, but we know that in terms about computational times, it's not the best one. So now I'm working on another research in order to introduce chance constraint inside the optimization, but also we could pass over robust optimization if necessary. And the last one is moving from transition power system, use the QDTR, but now with the thermal generator. So that means so that, for example, the profile of the thermal side of the generator could be analyzed with the QDTR. Dissemination. So 3 journals that have been published, and 3 that mostly coming in the next month. One is 99% with. The other is 80% that you see all the results about the last methodology. And now the last one is 10% that is about the chance constraint inside the power, inside the optimization. And 2 international conferences also. So this is all my results, and thank you, and sorry about the sound and everything about the sound. Do you know if necessary to move that to that part?
Yeah, let's verify that
I think that the more important is that first you do the exchange with the member of the jury distantly, because it's Fabrizio and that are going to ask the first questions. Can you hear us, Fabrizio?
Yes, sorry, the microphone was switched off. Yes, I can hear you very well. That's just it. Shall we start?
Yeah.
So, Sergio, congratulations for your excellent presentation. Very good job you done. Everything was clear. Your presentation, And I would like to congratulate with the topic, with the presentation, and with the results. So this, I think, is important. I read your thesis, and now I listen to your presentation, and I have just a couple of questions to start the discussion. The first, well, the first question is about the distribution, because you mentioned that you studied also distribution systems, and you have seen that the impact, you showed us the impact of PV in distribution grids, and then in the thesis you presented a long-term network expansion planning that is probably designed for transmission systems, not for distribution systems. So any idea on how to move from 24 buses to 1,000 of buses, because this is the main difference. And okay, there are some many other differences in terms of power flow, you radial networks instead of meshed, and so on. But if the most impacting difference is the size. So is it possible to scale up your methodology for distribution applications?
Thanks, Professor Pilo, for everything that you said before. And in order to answer the questions, yes, but let me explain first how will be, or the main challenge that I had with distribution, different with the transmission. This is a model that depends about information, and the information is related with the description of the asset, meaning so that if we have fewer or higher voltage cables, meaning that the area is higher, meaning that the thermal rating will be reduced, the influence of the thermal rating. Reduce conductors, for example, that could be used in distribution, the temperature of the ambient and solar radiation will be higher. So from the component side, the difference in between my methodology is mainly is how it will be influenced in terms of areas. So this is the first thing. The second is that to move forward is in the optimization side. My optimization mostly using my thesis is a thermal expansion. It's a transmission expansion plan, and without generations. However, distributions have another influence and constraint to consider, for example, the ACOPF. So my next forward is made a new, maybe network expansion planning, but mostly for distribution that take into account also the losses inside the lines. So this will be my first fix. So I don't know if I answered correctly about the different kind of component model and also the difference in between optimizations.
Yeah, you answered my question. Yes, thank you. That's sure. This is not the question was not related to what you have done, what we can do for the future, because most very high rates of investments are expected in the distribution system due to the transition, and then I was thinking how to manage in the distribution. But coming to your thesis, I have one question that is related to your slide number 28. If I'm not wrong. Anyway, is the slide where you describe okay?
Like this.
Yeah, this one. This is about the risk management, the integration of Monte Carlo in your network expansion planning. So the question here is, how can you manage with this algorithm the new lines or the changing of a cross section on the existing line? Because if you change something, I don't know how this method can work. If everything is stable, it works very well. But because if I understood properly, when you find the new F after the risk analysis, then you start this network spatial planning, and this means that you cannot update F for new lines, but the algorithm can decide to use new lines or to connect to new nodes or new node, so a new bus. So how can you can manage this in the future? I'm sure that you are aware that you cannot do that, but is it possible to manage in the future?
So, this about topology optimization also.
Yeah.
So yes, Professor. So yes, indeed, the moving forward is trying to move from Monte Carlo to another optimization method that led me also to calculate the new topology inside the control. So let me explain. You say the truth about how the methodology per epoch analyze the actual network. So means if I actualize the network, it's in the next epoch where I started to analyze the network with a new line. However, during the same epoch, this specific methodology is not doing. So the idea now is for example, first introduce an approach that is more topology based. So instead to have from the beginning the possible fusion lines, that the algorithm also select what is going to be the best route for a new line, not the possible that is coming be from the beginning of the determination. And second, if we continue with the Monte Carlo, it will be interesting also to introduce maybe a sequential Monte Carlo in order to analyze how it's going to be the changing between each step. So maybe in this changing between the step, I could see the new line, and in that way, I could prevent to wait until I do the network expansion plan to see the results of the influence of the new line. So mostly with these two.
Okay. Just another question I was thinking about that's because if you this is something that you have also proposed in the conclusion. Your plan is to move from DC OPF to AC OPF, and but you are using the OPF not only for the operation but for planning. So that means that you are using the problem is at least a mixed integer, and sure it is not linear, and probably non-convex, particularly if you consider that the companies have only a small number of cross-sections, standardized the cross-section they use. So this probably makes the problem convex. And so that's the question is, do you think that we can really use analytical methods for long-term planning with the AC OPF, because you need a lot of transformations, so band transformation, linearizations, and in any case you need many heuristics. So that's probably we have to do something different. I don't know, but this is a research question. I don't, just to understand if you have started thinking about. And I have also another question related to the Monte Carlo. And the second question is on Monte Carlo is that when I was reading your thesis, I thought, why not using sequential Monte Carlo? Because there are a lot of temporal correlations. Particularly, I was thinking about heat waves and the impact of heat waves on capacity and ratings. So you decided for the classical Monte Carlo. I'm sure you have right, but I just know why you made that decision.
Yes. So first question about the ACOPF. The answer is yes. Some researchers had done before that. However, the limitation of that research that is mainly accomplished to analyze maximization of the line. So meaning so that they want to control how much the DTR could increase the line. So let me show you here, for example, in the right part, they're analyzing with advanced constraint a specific maximization of the control of the line. The tricky part that still I'm trying to solve with the professor in Spain is how to include also the control of the temperature at the same time. And this is the second and the third study that I show you here. If we want to manage to include that, we also need to include the thermal balance, so it's more non-linear and more non-convex, the solution. So, to introduce the AC part and OPF have been done before, and yes, it's possible. The tricky part here is the introduction of the thermal balance of the DTR that should be solved maybe with some linearization, but with that also we lost accuracy. And the introduction of the chance constraint, for sure, it will help us in order to be in a safe zone. And the second, Monte Carlo non-sequential. I will explain with the maybe my thermal models. So first, it's about the temperature. If we take Monte Carlo non-sequential, the best way to analyze it is over a day, because we need to introduce how the heat of the previous state will be influence the heat of the next step. So talking about thermal rating, no? So we need to accomplish to accumulate all this heat over the day using Monte Carlo non-sequential. However, using Monte Carlo non-sequential also introduced me to me in a new subject about the, I don't know, generator scheduling, different kind of methodology that will be improve the accuracy of my model. So the other thing that I have with Monte Carlo non-sequentially about the cumulative distribution of the temperature, for example, is the effect of the PV and let me show you. It's the effect of the PV and the wind over the line. I'm going to here. This. It's because if I had to introduce the connection not only in production but also in how the temperature of the ambient and the solar radiation will also affect the PV and the wind, make that, of course, that if I do this, it's not possible because now each scenario will be correlated. So I cannot make a simplification about the probabilities. So the thing about Monte Carlo non-sequential first is how to gather to introduce the thermal inertia of each component every hour. So my solution is doing daily instead to doing like a weekly, but I'm gonna less the scheduling of the week, but still I'm gonna work in daily. And the second part is trying to solve how to deal with the interrelation in between PV, wind, and cables with the weather, because all are with the weather, all are interconnected. So I'm gonna give you an example. If we have so much temperature, for sure the efficiency of the PV will be reduced, but also the efficiency of the cable will reduce it. But also, if I have high solar radiation, the PV will increase better, so the cable will reduce it. So I don't have now how to deal with the non-sequentiality of that, the sequentiality of that inside the optimization. But it's possible to be done, but it's important to realize that only to arrive here to this chart, it took us like 1 year. So move forward needs more years for sure.
Yeah, that's just to conclude. Thank you, Sergio, for your presentation. I have many. I would like to discuss many things with you on this thesis, but I think it's time to give room to other reviewers. So thank you very much from my side. It's as a planner engineer, I really appreciate your effort to have you know, risk in planning. But this you can place the risk in planning without using a risk. That's strange to explain, but you know, planners don't want to use probabilistic methodologies, even if they have. I'm pushing them to use probabilistic approaches for planning, but because this is what we need in the distribution at least. And with your methodology, we can add risk and we can include the rating in a different way without changing too much. And so this is a very engineering sound approach for thank you very much, Sergio, for your job.
Thank you, Professor Pill. Thank you, Professor Pill.
So I think now we can go to the discovery. Can you hear that?
Hi. Are you hearing me?
Yes, Professor Sita.
Okay, thank you, because I believe I have a fluorescent image, so I was afraid not to be here. So I want to say good morning to everybody, and I want to thank you for the invitation to take part of this jury. I'm very pleased to be here to have analyzed the thesis, and I am really sorry not to be able to take part in the jury in person. It's always much better, but unfortunately this time I had to take another commitment, so I have to be remotely. I apologize for that. I want to congratulate Sergio MONTAñA SALAS because your presentation today was really very, very good. It was very clear, and I believe you have been able to organize all the material you put in the presentation in the best way. So it will be not only very clear, but also very comprehensive. We know that the research work behind the thesis itself, the document, is long research work, several years, a lot of information, a lot of results. And I believe your presentation was really comprehensive and really useful. So I really want to congratulate you on that. I also want to congratulate you on the results you have from your research. These results are really significant. They are in fact quite interesting. You have been able to touch very different points that are needed to address the research questions that were directing your research. And I believe, in fact, you had to master a lot of different domains to do the research itself and also to obtain and then to analyze your results. Of course, this kind of work and the results that come with it are always a good matter for scientific discussion, not only scientific but also technical discussion. And I'd like to put you some questions. I have already been putting apart some of the questions I have prepared, some of them because we won't have the time today, some of them because Professor Pill also addressed those matters, so I will try not to repeat too much. The ultimate goal of your thesis is in fact to develop a methodology to support system planners, right?
Yes.
And I'd like to, correct, and I'd like to ask you today, when you look at your work, what you have developed so far, what would you see as the required steps so this methodology can in fact be used in practice by these system planners? Do you believe there are much more steps needed? What kind of changes, what will be your advice for using this methodology in practice?
Thank you, Professor Sita, for all that you said. And in order to answer this question, is first the data. If I want to introduce more clear results, I need to interact with a specific planner with the real data. So if we manage to have a more precise data about the components, for sure we're going to have more accurate results. This is the first thing that is a challenge for me, trying to find data. The second part is about the methodology. So the use case in a methodology for a planner is either taking a seasonal pattern, for example, winter and summer, in order to gather the ratings, or either take a robust one that is one fixed for the whole year. So that are the two methodologies that usually the planners use. So the thing that the QDTR, as a difference of the DTR, is the QDTR let you to have in advance a stable ratings, meaning that it's not changing every 15 minutes and every year. That is a problem that have the DTR when you plan the future. The stability of the rating of the 50 year, when you change, for example, for every 15 minutes, a planner is something that is going to say that is not something that they like a lot. So the stability of the QDTR helps a lot, indeed, or only to introduce inside any network expansion plan. However, when we started to introduce the risk methodology, that part in a real planner way will be more complicated, because first is about the maximal events that the specific component should be sustained. So we put it an academic value that's 600 every 40 years, but maybe when a planner talk with a manufacturer, said, 600 could be too much or too many. So all these bones that I'm taking into my optimization, my method, should be reviewed by the real planner in order to see that that bones is in the real world working. And of course, this methodology will take a lot of efforts in computational side, so it needs to be improved if we need to put it in the future. So Monte Carlo is a benchmark. It's nice to have it, and will give you a pattern to go to know how to advance in the next. So as a conclusion, the way that I'm seeing QDTR is a mix in between the statical or the static rating or seasonal that the industry use, that's coming from the historical, and the real DTR that in order to use it, you need to deploy sensor and different software together. So with the QDTR, you analyze the grid and you know which lines could be more affected about for example, climate change. And after you analyze that, you put it the real DTR inside your planning and you solve the problem. So imagine the QDTR as trying to reduce the distance in between the static and the real DTR. So this is the way that I see the QDTR.
Thank you very much. Very good insight into these aspects of the problem. Now, maybe if you can put there the slide you have shown about the publications that you prepared.
Which applications?
The publications, the papers. Yes, the papers.
Yes.
Yes, this one. So first of all, also to congratulate you, because in fact you were able to put a good effort on the publication part to disseminate in scientific terms your results of your research, the models that you are proposing. So I believe you have 3 published papers in journals, right? The 3 first ones you have there, 2 of them as first author. And then in the thesis you said you had 2 more, but now I see that you have 3, right? And you have also 2 conference papers already published. Can you explain us a little bit more about those papers that are not yet published, that you are preparing? The first 2 ones, in fact, are almost there. They should not be so far from submission. Can you explain us what are the results that you are about to include in those papers?
Yes, Professor. And thanks. Okay, the first one, that is the use of the optimizing distribution planning with the long-term ratings in energy transition, is the results that you see here in the distribution side. Sorry, I'm coming back. Here, those results. So in order to explain better the methodology used here, it's in the first one. It's used with the Monte Carlo in order to analyze how it's going to be the technical violation in a lower voltage. So here, mostly we analyze the ratings over the power transformer that is connected with the medium voltage and the overhead line that also are more congested. So this is Monte Carlo mostly to see what happens if we introduce more PV and charging station. How will be constrained the network? And the second of the distribution part here is more a probabilistic network expansion plan that is well established. I've been working with this probabilistic network expansion planning long term. But the main idea here was the introduction of the QTTR to see what happened if I introduce a new rating methodology. So the result is like with this kind of rating methodology in this medium voltage network expansion plan, we could reduce the investment. And also we see the trade-off of the QTTR that they are not only expanding the capacity, but also analyzing these sensitive areas inside the PV production plus hotter season. The following, that is 80%, is this methodology. Is mainly the method that I show you here, the temperature basis constraint, and the results that you saw in the thesis are the results of this paper. It's in the 80% because still we are trying to improve the message, because as I said before, that take us 1 year in order to understand this. So it's gonna take like more time in order to try to explain. And the third one is a publication that I just started like a few months ago, 2 months ago, with the 2 engineers of Spain. That the idea is trying to introduce the chance constraint, but not the typical chance constraint that is showed in one of the papers, that in order to constrain or to analyze the maximization of the capacity, but also introduce a joint chance constraint that led me to analyze what happened also if I consider the temperature inside the nodal balance, for example. But still, we are arguing how to do it and how to do it really well. So for that reason, it's in 10%. Will be released maybe in, I don't know, in some month.
Very good. Thank you for all that detail. And maybe now we can discuss a little bit about that future, because you have this planning methodology, so we are looking into the future, right?
Yes.
And in your thesis, you address it in many ways. Of course, you present, for instance, the need to know about the demand in the future, which is always difficult. Not just because we are somehow trying to have accurate results for something we don't know really much about, but also because we are now going through a very different context than we was, let us say, 5 years ago. Why? Because we have this climate change, we know about it. We don't really know about its evolution. We know it is there, but it is still difficult, very difficult to realize what the evolution will be. But also, for instance, about demand in power and energy, namely for electrical energy, is changing a lot. It would not be so difficult to forecast demand for the future. I would say 10 years ago. Right now, it may be quite difficult because we have these changes in this climate, and the change in the climate, of course, has an impact in the change on demand for electrical energy. But also we are seeing a huge increase of demand for electrical energy due to data centers and due to the intensive use of very complex artificial intelligence models, right? So we will see in the next years, I believe, maybe a huge increase overall in terms of the demand of electrical energy. And this changes a lot of our way of looking into the future, because till now we have been seeing more and more renewable-based generation. We have been seeing also distributed generation of electrical energy. But with this huge increase in demand, now we see that we have to install new power plants. We are looking for nuclear power plants again, where we would not guess that they would be installed. So it's completely different. How do you believe that this change will impact? Because in fact, we thought that maybe the network, the system, in terms of the transmission lines and even distribution lines, they could be somehow alleviated by this more local production. But in fact, when we see this increase, we need again more and more capacity in our lines. So how do you see this difficulties, and how do you see the methodology that you propose to be able to adapt?
Yes, thank you, Professor Sita. I'm gonna stay here in this slide because for sure I will try to use it in order to explain myself as better I could can. So yes, indeed, future in long term, when you say long term is more than 50, 20 years, is difficult to assess. Even the weather is changing a lot. So when we start, first we need to visualize first the socio-political matters that also change this. So for that reason, we come in here for these trajectories. These trajectories have been evolved for, I don't know, for 15 years, and now they are with the socio-political trajectories of 2.65. I don't remember the number exactly, in order to understand what happened with this, that specific increase of the demand. So the main idea of my investigation is like I'm trying to suit it inside the weather. Of course, if I use less coal, meaning that I'm gonna have less emissions, meaning that I'm gonna have less temperature, for sure my network is gonna be less stressed. But mainly the result that I have seen is when I started to have this, as you say, this distribution network, when I have PV, normally the PV is connected with a transformer. And the thing is, when I started to put inside this transformer more PV, meaning that the transformer is going to be more constrained. So in addition, if now I'm going to have more demand at the same time for that specific scenario, 2.6, because it's coming more electrification. So now we're going to use better our transport, for example, and we're going to use better our way to produce energy. So now we're going to use more renewables. That meaning that at the end, the trade-off in between weather and flow even could stress even more the network than in the high-end scenario. So how I deal with that? I will let that I will try to work with the climate scientific that for sure they understand better the weather, and they study every time what happened with this transition and what happened with the socioeconomic pattern of each region, because each region is gonna have different pattern. And to try to fit my methodology as close as possible in the trajectories. So, for example, in the last study, I used all the weather from a specific socioeconomic pattern, but also I mix it with the expansion of the region of France. So I took the information from the operator that how we believe that is going to be better the expansion of PV and the demand, and I took the weather from the scientific part. So it's a mix in between two data sets in order to find out a solution for the future, because it's difficult even for me trying to understand it and for many scientists. So this is the way that I'm trying to solve it, Professor Sid.
Thank you very much for the explanation. I follow your ideas and I believe so I'm looking at the time. I believe we don't have much left. I just would like to pick here a final question, which is about, in fact, research questions. Today, looking back at everything you have done and looking also into the future, into what you are working and what you see as very important for next year, if you had to choose only one research question, what would be about this very important research question in this area?
Professor, could you repeat the question, because it was in between bad communication? Like
sorry for that, very sorry. I was asking about research questions. Today, looking at the results you have at the current state of the art and looking at the future and what you find very important to do from now on, if you had to choose only one research question now, what would that research question be about?
From my previous or a new one? A new one?
A new one for the future.
Okay. For future, I will stay here in this landscape because this is a landscape of the research. Of those, I will stay. I will maintain my research question in how to improve to calculate the rating in advance for a few decades, like how to gather this the rating using future scenarios. Why? Because for me, is this still the missing question inside the industry, like how I deal with my ratings without using historical. So this is something that I try to approach, of course, with the QDTR. But for example, I'm going to give you an example here. This ambient influence rating is an approach that happened in the United States, have been improved over 15 years, and still they are improving. And this is the way that they plan the future. I will do the same. I maintain in my QDTR trying to solve how to calculate in advance, but this time trying to put more uncertainty inside my model and trying to find more stable and help the industry to put it inside the optimization problem.
Thank you very much. I want also to complete this discussion, congratulating you again for your work, your results, and also to congratulate your supervisors, because of course this is not only the result of your own work, but also of their supervision. So congratulations. And I will pass the word to our president. Thank you very much for this nice discussion.
Thank you, Doug. I'm going to back to Frederick.
Thank you very, very much for your presentation. I thought you did a great job. I thought you brought the pieces to life, which was really useful. And I also know that the publication record is pretty strong thus far, and it has potential for further development immediately arising from this piece. So that's really great, right? That's very important. Some of the questions I was going to ask are maybe taken, but I'm going to do my best. So my background primarily is distribution.
Okay.
And even though I know a little bit about transmission, but you have a transmission line there in figure 2.2, and I can see as you move across the color changing, is it?
Yes.
Yeah. You have that somewhere. So and I suppose that's primarily related to ambient temperatures.
Yes.
Yeah, as you move across the degrees of the
Yes.
there. Yes, that one.
Yes.
Yeah. So in distribution networks, the temperature of the conductor is often very local due to geographical or topographical issues. Okay, so is that something you've considered at this stage, or is it something you might consider in the future?
Thanks. And I like this question because I know that you talk about overhead lines, but I would love to answer it in underground cables better, because distribution is mostly underground cables also. So first of all, we ended by the overhead line. So the spatiality, when I said that here I analyze the spatio-temporal of each segment, meaning that I'm taking not only the temperature, I'm taking discrete. So I'm going to give you an example with transmission, and I'm moving forward with distribution, because I had to understand that when I did my research about distribution. A transmission, when it crosses a valley, we have high wind. It will be really hot, but a high wind is good. And instead, low wind and the same temperature is really bad. So the same line that is crossing one valley, one mountain, in the mountain could be like this, and in the valley could be like this. So this is the geographical part that I'm using in my investigation. Now in distribution, when I started to analyze the distribution network, the first challenge that I accomplished to me was in the overhead lines. Is that now this is a bare conductor, and in distribution, mostly you don't have bare conductors. You have conductors like this. So maybe it's XLP or it's not XLP, but it's covered. So when I started to analyze the thermal model, the thermal model that I use is an extension of this thermal model in underground cables, but now influenced by the solar radiation and the temperature. So it's a different model. So mostly I would say that the tricky point here in distribution is to know if the line is backfilled or is not backfilled. This is the first question. And when I ask it to the distribution part, they say, do know. So if you ask me if I plan it, I will do it with direct bullet, because in that way, the seasonal pattern will be influenced. When you put a backfill, it's in order to do a to maintain the thermostable stability inside the cables. So you are losing mostly all of those impacts. So when I started to plan, I said, okay, you don't know, I'm trying to put my worst case that it's going to be direct body. And in that way, I consider how it's going to be my soil moisture risk. But my second question is, do you have any data about soil moisture in this trench? And the answer was no. So that is going to be more tricky, and to know which kind of soil that I have, because this part depends on the soil taxonomy. So if I have I don't know, clay, and I heat the clay, it's going to be so different than I heat I don't know, organic. So this is the tricky part. So the answer is yes. When I start to analyze distribution, I move forward from this to the overhead line, but still maintaining this. And the tricky part is trying to find all the data of the soil. So that is something. But this is overhead line. Distribution also is transformers. So when you move forward from transformers, and the first question is which transformers you want to analyze. That the one is on the pole of the distribution. So they say to me that mostly that is going to be congested is those that is going to be in the distribution side, not in the distribution from the residential part. No, is that they make a connection in between voltages. So huge. So when you have huge transformers, also depending on what kind of influence of the cooling will be taken, the result will be different. So everything is about information. The model is already set, but everything about information. And the geographical points could be solved by the model, but with good information. I don't know.
I suppose I just share in the UK and Ireland, there is lots and lots of MV and even LV overhead line and even HV overhead line. So it's quite different to maybe the continent.
And better.
Fair, yeah.
Like without cover.
Wolf and stuff like that.
So
ACSR.
yes, so it depends. Also, is the height. It's because in the model, if I started to show all this model behind this, it's also the height. So it's different the height for a distribution that could be, I don't know, residential, because distribution residential also. But also this height would be, I don't know, 50 meters. The height depends on the wind. So everything is crossing.
Yeah, perfect. Thank you. So the next thing I'm going to ask about is a lot of the focus, all your focus is on planning, right? And which is great, and planning in the context of climate change. And one thing that I'm very interested in is integrating flexibility and storage and things like that into the planning of systems. How would you feel that these sorts of new concepts in planning would fit into your approach?
But could we talk on a specific concept?
Let's say, for example, maybe a demand response for EVs or something like.
Okay, demand response. So it depends how we're gonna use the load. Okay, I'm gonna give you the best answer from me for that. So the thing about the demand response, because previously I made investigation in Colombia about demand response, and this is about also the people, and the people they like to use or not use. So it's difficult even to forecast. So I will try to explain in a seasonal pattern. So let me show maybe here. So imagine that now I'm trying to understand seasonal patterns, but another influence in the forecasting side, because when I was trying to do forecasting for demand, now is possible events that maybe change that. What I explained to this, that normally the people when arrive home, what they do, they cook and they charge the battery. So normally, or when I try to here, I'm gonna be in this. So normally, when that happens, in this specific network, this network of here is a residential network, and this network here is a residential network. So we have similar patterns in the way that they use the energy. And this is a urban. No, sorry, urban, rural. Urban, and this is rural. So here, the way that I introduced KDTR for that specific lower voltage, I started to see what happened in that specific lower voltage, and they have more problems with the overloading than stability, because we know that distribution they have a lot of problem about the stability. Most, not so many about overloading. So when the network is a specific network, residential, that also have a PV connection, and the way that they use the energy is with charging station, the way that the QDTR allowed to, trying to make a trade-off over there was during the nights. During the day, the QDTR is not doing anything. It's not constrained. It like could be the seasonal one, and it's going to be the same. But during the nights, the QDTR allowed to reduce over 60% of the technical violation in this specific network. So this is the way that I try to move forward to apply. Of course, I cannot say that for this is a specific demand response, but I try to put it like in the same pattern, the distribution plus PV plus charging station.
Very good, thank you. Next question I have is, yes. So you talked a little bit about aging. So aging of components, and so it is in the expansion planning, can the QDTR account for aging of individual components? Is that kind of included in the expansion planning approach?
It's not. It's not. It's something that I should put it inside my perspective. And you're right. The aging is for me is an easy move forward, because the aging depends on the temperature. So if in my expansion plan doing Monte Carlo, I have thousands of realization only to know this temperature, the calculation of the aging is taking all this formula back. So that meaning that it's not a constraint, it's more a result until here. Here, the aging is a result of the temperature. So I control the temperature, meaning I control the aging until here. But the right way to do it is trying to use, in order not to move forward, remember that studies that introduce the thermal balance inside the constraints?
Mm-hmm.
Is to introduce this as a constraint inside the optimization and add another constraint about the aging. So temperature, aging, correlated but different constraint. So
it would be a little expansion of what you've done already.
Yes, but it's going to be an expansion, but it's more about how many hours do you want that this temperature increase and how much is the quantity of the temperature. So aging is related with frequency and the delta.
Yeah.
So will be like this. I don't have the answer yet, but this is something I need to move forward.
So so do you think in your framework, you've probably talked a little bit about it, that you can apply the framework to both transmission and distribution? What do you think are the key differences in the implementation between the transmission system expansion planning and the distribution system expansion planning?
Normally, when you use the transmission expansion planning with DC, because the difference between the delta of the voltage is not included, is not so influent as a distribution. For the reason in distribution, you oblige need to use AC in order to see the difference of that voltage. So the first is taking into account AC OPF, no DC OPF. Normally, I could say like mostly all study with the transmissions with this. So this is my first difference in between those two. And of course, the length of the lines. So we remind the first studies about DTR, they talking about the length and how the thermal influences started to move forward from 80 kilometers from the over analyzing the temperature, and over 80 kilometers, you need to also analyze the delta of the voltage, of the angles of the voltage. Mm-hmm. So these are the two main key differences. So you need to include the losses. You need to include also the constraint about the angles inside the voltage in order to see the stability of the network in this distribution. In transmission expansion plan, you could simplify, no simplify. You could use linearization in order to avoid that. So this is the main difference between those two. So that meaning that when I do it, the QTTR, I'm taking only the part, the real part of the resistance in order to calculate. The other is the nonlinear part.
And what about the risk?
Risk about what?
Like is there a big difference in, or I suppose this could be dictated by the system operator that's carrying out the study? Is there a big difference in the risk that one should consider in the QDTR between the transmission and the distribution system?
No, I got it. No, my risk is related with the temperature. So it's not how much I related to how much hours I allowed in the transmission, how much hour I allowed in the distribution, is how much temperature I allowed. So it's this risk is directly related to the temperature of the cup. So if I let that some hours started to over this, I could risk to reduce the lifespan of the network. So should be the same because you are risking an asset. So how much do you want to risk the asset? Mine is about temperature.
But is the risk related to the number of customers connected to the asset?
Until now, no. Until now is the temperature is related with the demand. That is the I over there, the current. So for sure, it's not directly connected in the optimization, but indirectly connected in the answer. So meaning that here, when I take the I, is the demand. How many clients I have, more demand. And the temperature at the end is the weather. It's a mix of the two. So for that reason, my answer also with temperature, because the temperature takes these two, the demand and the weather, in order to calculate. So my risk is how much do you want to increase the temperature? More than this.
And I've one final question. Sorry, Ron.
No, it's okay. It's okay.
Very your work is very comprehensive, and it's covered a lot. But because it's so comprehensive, it actually makes you think about a lot of questions.
Yes.
And so one of the things that in my country we're particularly concerned about, we're not really that concerned about temperature rise. We could actually do with some temperature rise, in fact. But what we're more concerned about is probably extremes. And one of the things that is a potential scenario for climate change is not just an increase in general temperature, which has an impact on the rating of the device, but the increase in extremes. And is that something that you're thinking about for future work?
No, indeed, it's already done. It's not a delta of increase. It's my rating here. This I'm taking the strings. Always I'm taking the strings. And here, for example, the extremes are 50 years. It's not the extreme of 1 year. It's the extreme of 50 years. So this, I don't know, 28, 30 observation is the 30 observation of the extremes over 50 years. And I do the same for the future. So I know that always this delta is moving forward, but I am only working on that.
But I suppose what I'd be talking about would be that, let's say, for example, the average temperature of a country might be increasing, right? But the peak temperature, let's say, for example, in the UK, I think peak temperature ever recorded until about 3 years ago was 37 degrees Celsius. And then about 3 years ago, we had 40 degrees Celsius, which is a significant increase over what the long-term average was, long-term peak was. So the potential direction of travel for weather is a peakiness, an increase in the peakiness, and that while there is an underlying change, the extremes will become more extreme. So as
super quantile, like the lowest quantile.
Yes.
Indeed, it wasn't my my investigation. It was a previous investigation. Of course, Andrea has been working on that in about super quantiles, but it's more in about no long pattern they use for short term. So they are trying to find these super quantiles in order to rather the ratings. As you say, I'm using for long-term patterns. So I only can analyze the extreme hours
Yes.
inside
From the previous 50 years.
on the next 50 years. So it is only like this. But yes, maybe something in super quantiles in the middle, but I really don't have how to put it now.
Yeah.
But it should be something like that.
So again, I'd just like to thank you for the great presentation and very well presented, and you dealt with any technical issues very well.
Thank you.
So congratulations.
Thank you.
Okay, so now it's your turn.
So I start to thank you also for your presentation for me really years, since your manuscript. And we don't know, but after you sent me an invitation being part of this committee, I met Andrea and I asked her about your work. You made it like that, which in Italian means that is, you are very good. In fact, I agree with you.
Thank you.
Your work, very good like that. Yeah, so we know, and this means that your work is very good. Personally, I appreciated the multidisciplinary and the electrical systems, revealing the components. And then we pass to data science, statistics, and then there is decision making and optimization and the perspective if you want. And it was nice to read your thesis in the sense that you really know how to tell a story, set operations, and its answers arriving little by little. And this system that becomes more and more complex.
More complex, yes.
And so, due to my background, so this makes me to ask you about the complexity of the optimization problem that you have to solve. You commented a little about that, but I really would like to know about the dimension, the scale, the horizon, and the computational time if you want to solve.
We're going to talk about the optimization, so I need to show you the optimization.
Yeah.
So let me 1 minute, because this is the last paper that we are doing with Andrea. So give me 1 minute. Open. I'm waiting for open the PDF. Because, sometimes Acrobat is taking. No. Indeed, my optimization, here we are Roman. The optimization that one do it every time for me is like, the child of the optimization. So I will show it. So I will put it here in order to show it really fast. Here, okay. So this is so small that. So this is a multi-period optimization. So that means that I'm taking epochs in order to analyze 5 years, and each epoch have a decision model, and inside each epoch I analyze every hour, and inside each hour I run the Monte Carlos. So the Monte Carlos, if I have, I don't know, 8,700 per year, I have to run for each 8,800 per year a Monte Carlo, and each Monte Carlo need to be verified by the auto sample. So I started with 200 Monte Carlos, but if it's the auto sample have done the same risk scenario, I need to increase. and the auto sample is 2,000 Monte Carlos. So the 10 times. It's always, if I 300 Monte Carlos, it's 10 times 3,000. So I'm telling you because the computational time is harder, and it's because the Monte Carlo is not included here. It's only a module external that's going to analyze how it's going to be the network and it's going to be the results. So here is from the terminal point, it's not a stochastic, so it's a deterministic transmission expansion plan, multi-period, that is influenced now by the good timing, by the load sharing, and the CO2. So of course, if I need to put the CO2, otherwise, if I need to see what happened with the PV. And for the lines, I use a linearization here that is in order to try to linearize the losses. So I'm calculating losses, but it's not a constrained site, it's an output in order to see what happened with the losses also. Also is included here. And in order to control the investment in between epochs, I have another control variable that is going to be the cumulative. So that meaning that if I'm building a new line in the epoch 1, should be built in the second one, should be considered as a binary. So, and the increase for demand and loading, and this is with a specific formulation, the rate. So I have rates for demands, I have rates for wind PV, I have rate for everything, and everything will be evaluated by epochs of 50 years until 2050. So there are 10 epochs.
That's the outside.
A good question.
And you solve it, it's a non-convex, right? You said it's non-linear.
A MILP. A MILP.
MILP. And
a GURU, yes, I'm using a GURU Pi. Yes, I'm using a GURU Pi. And why? So if I want, I like to talk. I like to talk. It's because when I started with this, I started with PIPSA. PIPSA runs by their own model. And I moved forward to Panda Power in order to try to model with Panda Power. And I tried to run the OPF with Panda Power. When I started to see that Panda Power could be really slow, I moved to GURU Pi. And when I moved to GURU Pi, I learned that GURU Pi could be 10 times faster than Panda Power. And only trading in between optimizers. And each one have their own optimizer and their own methodology. So how I did that? I used if you go to GURU Pi, they have a nice model of OPF. And I started from scratch a year ago. And this is the evolution of the GURU Pi OPF. So in that way, I started to put contingencies and lots. Yes.
And so the other question said is about the machine learning. So we finished with the presentation with the other subject I'm interested in. So the machine learning models you use them for a couple of frequency and to model. And my point is, how many times you need to train these models? Because you work locally and then you have this European scale. So did you use kind of cluster learning, or you have to train with these models each location?
Okay, so I will start with, I did several machine learning models indeed, but in my thesis I put the reduced one. So the most important one, of course, that I show it here is the moisture.
Yeah.
So first I started to see the observations. The thing about the moisture is like I had to say that we care about the first layer, because in this layer is the food. Everything is related with food. So in the first layer, we found a lot of observations. But we are in the fourth layer, that in deeper soil. And from, for example, 300 possible weather station open source, because I'm open source. 300 open source weather stations. I only found that only 32 have the possibility to gather either temperature and either moisture. However, I it will be more complicated than only the observation. It's because maybe I pass really fast, but one really, really important part plus the soil moisture and the soil and the soil temperature is the type of soil. So how I deal with that? I need to understand soils. So besides all the physicals inside of evaporation, I don't want to go over there because it is another subject. I want to explain that we could classify by 12 types of soils, and I did it. I classified 12 types of soils. So I run for all Europe, all different kinds of data sets that give me the possibility to find out these 12 types of soils in that surface. After I got it, the possibility to do that, I try to combine the classification of these 12 soils with the observation. Because the soil is not only about clay. To talk too much. It's not only about clay, it's about porosity, so texture. So I had to mix composition plus type. So at the end, the machine learning model that I did is a combination between soil classification and the kind of observation about the temperature across Europe. When I was talking with Andrea previously about how I could improve this, is move forward than Europe, because the same data could be found in all world, and it's the same clay and the same porosity. The only thing over there is how much is going to rain, how much is not going to do. So to do that, I only showed 2, but I trained at least, I don't know, 8, 9, because XQs, trees, all this, and we made a nice picture that is in the thesis that is taking computational time plus accuracy. And the better one was this. So yes, I had to retrain it. And every time that I do it, I try to find out is the best distribution of the variables inside. So I had to do this temporal analysis in order to see how much, for example, the rain is going to modify the soil temperature. So I also did analysis of the temporality to that. So I feeling like I answered too much, but the way that I'm trying to explain to you is like I am not only taking one variable in order to train, I'm taking at least 25 variables in order to train the model. And each of those variables is a specific variable inside the nonlinear equation of the soil temperature, for example. It's one model. No, it's one model for all the 12 classification of soils. The soils is not. Yes, it's not related with the type of country. It's more with the soil.
About the long-term incentives. So you use the RCP, so different ones, and then but you said they just I could consider ensemble of scenarios. So these are models for long-term kind of data.
Yes.
So this means that you use only one model per RCP.
So I'm gonna explain a little more about that. That was a discussion that I had with an engineer that he's doing modeling for PV. It's in the next meeting. But the thing about the projections. So imagine that the IPCC create the projection. You know, the RCPs. We say that we need to be in this specific point for 2100. But they gave the the boundaries. We need to be there. So each lab in Europe, the Denmark lab, the France lab, release their own climatic model. So the answer is I'm using one climatic model for this dataset. But however, this dataset have the possibility to have at least 10 climatic models.
Yeah.
An ensemble. So the idea is if I want to move forward in about the sensitivity of the climate model, I will run the same with all 10 in order to see, the pattern.
Yeah.
Yeah, says this. Sorry.
I compare with a non-technical question. Saying, if you look back to everything you have done, with the knowledge you have now, what you would do differently? PhD path. It's not technical. It's not.
No, but it's technical because what I do different about my research.
Yeah.
I mean, I'm an engineer that like to study different matters. So I'm electronic electrician at the same time. I have also mastered in sustainability. So that, but all that, the most thing that I love is the optimization part. I really love the optimization because this is the best way to do it, the best way to do something really fast and really accurate. So I will do more time about my optimization, and maybe I could have the chance constraint here. My feeling is like I didn't have my chance constraint join with this temperature release it. It's like really a feeling like in my heart that is something left in. But it's going to be in the next publications. But it's about the mathematics, math behind this applying in optimization. Okay, thank you.
Okay, so I think now Laurent can ask you a question.
Yes, can you hear me?
Yeah.
Yeah. Good morning, Sergio. Good morning, everyone. First of all, I would like to thank you for inviting me to be part of this jury, because the topic is very relevant for RTE as the French TSO. As you may know, we own more than 100,000 kilometers of power lines, 7,000 of which are underground lines, and we also have something like 2,500 power stations and so many power transformers. So the questions you address are extremely relevant in the context of the energy transition and for RTE in particular. So thank you for your presentation, which I found very clear, and congratulations on the really great and very substantial work you have done, because you studied a lot of topics about optimization to climate change and so on. So it's very impressive, the amount of work you have done. I also appreciated reading your manuscript. There are just a few typos, but really nothing major, and I think it's very, very nice and very clear. Maybe I was lacking one table in the manuscript, which would summarize the climate data you use in each chapter, because you use different data sets depending on the part of your thesis. I think it would have been nice to have this addition. So I will probably send you a suggestion in case you want to take it into account, maybe for future papers. I had very few questions because already a lot have been asked, and Valentina just asked the main one I wanted to ask, by the way, which is about the number of climate models you use for the projection. So in the last part, so I indeed understood that you used only one of the 6 models that are available from the Copernicus dataset you used. So indeed, as you mentioned in the perspectives, you should, in future work, if you have the opportunity, you should consider using all the 6 models or even more models from different datasets. I just wonder, how did you choose the one you used for your evaluation? Was there a specific criterion for that?
Thanks. Yes, when I'm using Copernicus in order to download it. So when I'm trying to search a model that let me in the same model not only gather the wind, for example, for 10 meters and the temperature for 2 meters, and indeed precipitation and everything, is that a model that gives me all the variables that I need. So when I was swapping in between models, I found out that some of those models, maybe it was because Copernicus, they have some problem, I would say. I don't have the possibility to select all the variables that I need. So this was my first filter. as like what I need and what the model showed me, and if give me all, I will work with that.
Okay. Yeah, just for your information, so this Copernicus dataset you used is not old, but it was a previous one, and now there's a new dataset called the PECD, the Pioneer Plan Climate Database, that has been developed for ENSOE applications, and it's richer. There are more variables and more recent models as well. So based on the CMIP 6 experiment instead of CMIP 5 that you have in the one you used. You also mentioned that the model resolution is pretty coarse, so you have them at 25 kilometers resolution, more or less. And so, what do you think is the impact on your result? Because when you want to talk about overhead lines, for instance, you really add local effects that can be very important, which are not accurately represented by 25 kilometer resolution. Do you have any idea of how it may impact your results, or also said differently, what range of uncertainty could it add to your results?
Yes, and thanks for the advice about the new dataset. Yes, I feel like until now I have the possibility to download all the 3 scenarios. But about the resolution, when I start, I had to admit that when I start my investigation, I will start with reanalysis. That reanalysis that gives you the opportunity to go even to 10 kilometers. But when I move forward to climate projection, I feel the lack of resolution between 10 and 0.25. And when I say that I feel it, is because I'm telling you a story about the underground cables that is showing related about the soil inertia and soils. And taking a soil of 25 kilometers as a generalization is too generalized. And so trying to fit all the variables in 25 kilometers for underground cables and in distribution is even a problem. So yes, I feel like the resolution of the data for sure will change my results. However, if we started to analyze the pattern in 10 years or 50 years, 30 years, for sure, maybe like the temperature over the 25 kilometers could be relative similar each other to the next coordinate. So if I had the opportunity to have better climate projections with better resolution, like a 1 kilometer, because my database of the soils is the 1 kilometer, for sure I could see more variability inside the rating. And maybe in this variability of the rating, one of those extremes could be extended a little more.
Okay, thank you. And maybe one last question. So you, in your manuscript and in the presentation today, you focused on the end of the century, so the period 2080, 2100. Did you have a look at what would happen or what your results would give closer to us, let's say by mid-century, 2050? Did you look at all at that or not?
Yes, indeed, all my economical results are to 2050.
Okay. So yeah, just to summarize my analysis of what you did. So it's very interesting. The methodological developments are really great. I just emphasize that the uncertainties quantification due to climate change and especially to multimodal aspects and downscaling maybe to local effects and so on would be very nice to investigate in the future. This doesn't at all minimize the work you've done, which is really great, and I really appreciate that, and I would be keen to collaborate in the future because that's very relevant for what we're doing, and so thank you again and congratulations.
Thanks to hear that about the collaboration, because it's something that I want to hear a lot about these future possibilities with RT. So thanks a lot, Mr. Roman.
Then we need the last one.
Maybe there is another mic there.
Just speak loud because we just have to listen.
Okay, now it's working. Just a few questions. Thanks a lot for your presentation. It was very nice, very complete. A lot of details about the methodology, the results. So the literature review, I really appreciate. And there have been a lot of questions asked already, but still some more questions that are not answered yet, but partly answered. First one is about the kind of factor in the future that could affect your results that you've not fully modeled. I understand from this graphic and the explanation you gave to Zita that you modeled the different scenario of electrification. So different kind of EV development, electric heater development, and so that's done because I'm sure that affects the results. And my question is, did you look at different kind of demand side management strategies or potential? Because this, I think, can also change a lot the results if you're able to change the consumption to avoid grid constraints instead of having to use to
Yes. Yes, I feel like I need another GR for my optimization, and that feeling like the inputs outside my optimization. So the question is like I really try every time to isolate the influence of the QDTR because my objective here is ratings. So I really try every time to do it. So when all my results is trying to compare the same, for example, when I say historical and future, inside optimization, I use the same expansion for everything. So in trying to fit it inside the same framework in order to compare it. So in order to answer the question is how I did it, I use open data for the specific regions. So maybe it wasn't here, but a paper that I did with the interconnection between Italy and France. All the data is coming from NSOE, and how it's going to be projected, I use the RTE scenarios for France. So I remember that the eco mix, they give you the opportunity to have different scenarios for different kind of possible demand, and I run all. You know, I took M0, M1, M0, M1, all the combinations in order to see how it's going to be influenced my pattern with a specific RCP. Well, later I tried to see which of those expansions fit more to this. And this is something that maybe underline Logan, is that the next data set that now is available, trying to connect this, and this better. So the lack of the lack of resolution inside my model optimization is mainly due by I'm using the data that I could find as an open source, and I don't have any specific case. So, and the answer is yes. My results of optimization is really determined by the specific scenario, and of course, inside the scenario, it's expansion of the network. So I don't know if I answered correctly, or should I continue talking about that?
Okay, that's fine. Regarding, so I'm also interested in the distribution system. I fully understand how this works and this works today with the transmission system, but I'd like to know what kind of system operation. I think this one's a little bit a question of Zita also, but what kind of practical operation of the distribution system you foresee with that kind of tool implemented? Because in the distribution system, we don't observe everything. It's hard to operate all the loads that are connected. And
yes, indeed. I'm showing the results of the optimization that is not mine. The optimization behind all of this in distribution is an optimization done by the University of Cagliari. So I'm gonna, in the way that I understand the optimization, this is a probabilistic expansion plan. So they analyze how the node is going to be expanded using different kind of probabilities, and in that way they will find the best scenario in order to solve. So when I say expanded, it's PV contribution and different kind of contribution inside each node.
Yes, but for example, here we will take into account the possibility of having containment of PV, which is very huge levers to lower the investment of the distribution network. Once you start doing that, how do you coordinate with your because if you decide at one time to curtail the PV, it's in competition maybe with the
Feeling like these two kind of optimization is more trying to find a technical violation. So you see it always trying to find where is going to be the worst case inside the technical violations. The technical violation is taken not only for overloaded the component, but also by the instability inside. So that's where I don't remember now if the codeterminant is included, but I remember that it's more related with the how the grid is stressed. That is more my work.
So I think I will stop here and maybe let conclude with I guess no questions, but still remarks.
Okay. So yes, I'm not really making any question, just 2 or 3 quick observations, and actually precisely at 12 o'clock. So first of all, I would say that to say my congratulations to Sergio. In 3 years, I could see really how it was an incredibly hard working person, hard working in the numbers of our work, in the efficiency in the hours worked, with almost no procrastination. That is, it makes me wonder if he's really a researcher or not. I don't know, because of his previous experience in industry. And all these done actually with a kid coming and first month, kid that we're going to see this afternoon. So these are the extra stress and less hours of sleep. So this excellent self-time management and also the excellent supervision, of course, managed really to extract the maximum possible technical result that was possible in 3 years of work. Sincerely, you made the question of what to do different. A lot of things could have been done different, but not in the given time. We are really on the optimization, you are on the flat point, you are just moving around the optimum. Then just a little observation about what Laurent said about the more fine available resolution data, and actually that plug directly on the observation of the on the documentation of the peaks or the extremes in the future. So I will just summarize that this methodology actually integrates the increase of peaks in the future, as long as they are into the original weather climatic projections, they are already included. Because Sergio said that we want to check exactly the peaks. But there is actually something extra that can be done, and actually Sergio did it for the underground cable. I don't know if you can put very quickly the paper about the underground cable before. The methodology that he has developed for the underground cable to model better the soil dynamics, the soil behavior. If you show, for example, yes, okay. So actually, he let to model much more finely, with much better, much more fine resolution, spatial and temporal, the parameter that we are studying. So actually, one of the possible things that we have not done because of time, but could have been done, is to redevelop a machine learning of this type, but for the atmospheric weather, so the air temperature, the wind speed, the solar radiation, the clouds, etc. So to have an alpha an hour better resolution for apply to use instead of the climate projections. This would have actually lowered much more the actual rating. So this means that if we do an analysis like this, we will get a much more constraining rating, but more strong. So probably this is something that should be in a next future work with them. And I thank you for being here, and I pass the microphone to the president of the show.
Okay, so I think now we will have time to deliberate and
Yeah. I could go.
We don't have the paper.
yes,
I go to the
okay, so
we don't have the
it's the how to do Zoom. Okay, let's go in the other room. So you have to go for each of the you have to go, and Laurent, you have to go in the other team room.
Yeah, okay, no problem. See you in a minute.
Thank you. Thank you. But you're, yeah.
Okay.